All right, here we go. Section 5.4. This is factor and solve polynomial equations. So we need to learn some new factoring techniques. We've got some formulas coming at us. It's definitely a challenge. We will factor to solve. That is the ultimate goal, is to solve a polynomial equation. We have a bit of vocab here, so you're welcome to write this down. You don't really need to. I can read you the definition. The first two definitions are really to understand when we're done factoring, which is definitely something that will come up in the examples. So I'm going to actually just read you the second vocab, factored completely. A polynomial is factored completely if it can be written as a monomial or product of monomial and one or more prime polynomials. So again, you're never quite sure if you're done, and that's where these vocab words come in. Factor by grouping is a really wonderful technique to factor a polynomial of power 3, a third order polynomial. So this is a method used to factor some polynomials with pairs of terms that have a common factor. And then quadratic form. So we will use this as well. So this will be an example coming up, but we'll see a polynomial like x to the power 4, x power 2, and constant, and we'll use our quadratic techniques. Again, here we go. This is the definition of polynomial with one or more terms is a prime polynomial if it cannot be written as a product of polynomials of lesser degree using only integer coefficients and constants, and if the only common factors of its term are -1 and 1. So we need an example for this. So here's this is not a prime polynomial, this 16x squared minus 4x plus 8. And hopefully you're looking at it and saying, oops, sorry for the zoom there. 16, 4, and 8 are all divisible by 4. You could factor out a common 4. So this would not be a prime. And so also here, another definition of polynomial is factored completely if it can be written as a monomial or product monomial and one or more prime polynomials. So here, again, this looks, the history of this problem, you probably factored out x plus 2, and you're saying, hey, am I done? Have I factored completely? But notice that this quadratic could be factored a step further. So let's get into some of the, actually before we get an example, we should look at the sum of two cubes. So it's a nice formula. These are special factoring patterns. So the first one is the sum of two cubes. Again, a cube is something to the power 3, the sum meaning you're adding them. And then you also have the difference of two cubes. And again, you are very comfortable with the difference of two squares, but this is the difference, subtract, of two cubes. And we have formulas, and I'm sure you'll write these formulas on your formula sheet. I will also provide you these formulas, right, on our quiz, our test, even our mid-year exam. Those formulas will be given. So how do we look at this? Well, in the example, we have x to the power 3 plus 8. And the key for you is to recognize that 8 is really 2 to the power 3. So in the formula, a would be x and b would be 2. So I just plug into the formula. It says a plus b, so it's x plus 2. And it says a squared, which would be x squared, minus a times b, which would be 2x. And then we're squaring the b term. 2 squared is 4. And the difference of two cubes would look something like this for an example. So here, we'd have 2x raised to the power 3. So our a term is 2x. And 1 is the same as 1 raised to the power 3. So our b term is 1. So the formula says a minus b. That would be 2x minus 1. A squared would be 4x squared plus a times b, so that would give us 1 times 2x, which is 2x. And then finally b squared, and b is 1, so that'd be 1. Nice formulas. Again, sum of two cubes and the difference of two cubes. And so here we're going to factor using the sum and difference, a couple examples. I'm going to go through a little quickly here. Just we've already gone through two examples, but you can see here that z to the third, and part of this formula is just recognizing this is the difference of two cubes, recognizing that 125 is really 5 to the third, and then you just plug the values into the formula. Here is another example, and this one's trickier. Why? Well, you might not see it as the sum. I mean, there's two terms, and you're adding, so you're hoping for the sum of two cubes. But first, you have to factor out this common 3y. So once you do that, you're at this stage, and hopefully you see that 27 is 3 raised to the third, right? And you see that 64 is 4 to the third. So then you can use the formula and plug in the values. This is a trickier problem, and it's a two-step problem. First, you'd have to factor out the 3y. So why don't you go ahead and give this a shot. This is definitely a polynomial, x power 3. Looks like it's going to be the sum of two cubes. Go ahead and hit pause, and when you're ready, hit play. So there is the answer in red, right? Hopefully your first step was to factor out an 8, and then you could recognize that this a would be x, and b is going to be 2. And then I grab the formula right here. You would just plug into the formula and get the final answer. Again, final answer in red. Okay, so this is probably one of my favorites. This is factor by grouping. The way this works, this is a third order polynomial, and you're kind of looking for this. So what am I getting at? Well, you're looking at the first two terms and saying, hey, let me factor out x squared, and you're left with x minus 2. And then I take the next two terms, including that negative, and I would look and say, hey, let me factor out a negative 9, and you're left with x. And then multiplying what times negative 9 gives me positive 18 would be a negative 2. And now you're kind of high-fiving everybody because you're saying, check this out. I've got this common x minus 2. So it's a pretty unique. This doesn't happen for every third-order polynomial. But when it happens, it's exciting. So now you really look and say, I've got these two terms, and I have a common x minus 2. And so I factor that out, and I'm left with x squared minus 9. You see that? So again, I'm taking from the first term, I'm pulling out the x minus 2, and I'm left with x squared. And then I'm taking out the x minus 2, and I'm left with negative 9. Again, here you're feeling great, right? You've recognized this factor by grouping, but you're not done. And that's that whole vocab piece, like to look and see, hey, x squared minus 9, that's the difference of squares. So you have one more step. So always, before you decide that you're done factoring, really look at your final answer and convince yourself that there's not one more move that you could make. And so here, the difference of squares, and now finally, we are done. So let me go through this example. There's two here. The first one is, looks like we've got a difference of squares, if you can see that. Right, so you've got 81 x to the fourth is really 9x squared raised to the power 2. And 256, this is a hard example. 256 is 16 squared. I have a hard time recognizing those. But we do come to a difference of squares here. And again, because it's a fourth order polynomial, you think you're done. I mean, this is stellar work if you were able to factor this difference of squares. But notice here, this 9x squared minus 16, that's another difference of squares. So you would factor that one more time and you're done. So again, looking at this problem from the start, you're hoping, it's definitely not a difference of cubes, but you're hoping to make it into a difference of squares. And again, it is a square if you make x to the power 4 turn into x squared raised to the power 2. We'll work on those some more. And then the second one here is by, first, really your first step is to recognize the common 3 and also y to the third. So we could factor out this 3y to the third, and then we're left with this fourth order polynomial, but it kind of looks like a quadratic, right? It kind of looks like x squared minus 5x plus 6. So I'll use my quadratic techniques and I'll factor it. And again, nice move here to just, instead of writing x, we're writing y squared. And you can check this, right? Multiply y to the squared times y squared, and you will get y to the fourth. You'll get negative 5y squared when I do the middle terms, and finally negative 3 times negative 2 gives me positive 6. Am I done? Again, can I factor any further? These look like difference of squares, but 3 and 2 are not squares, so yep, you are done. But again, very cautious to finally say I am finished factoring. Hey, why don't you give these guys a go? I think the first one is going to be a factor by grouping. And the second one looks like a factor using quadratic techniques, even though it's a fourth order. When you're ready, hit play. And there are my answer, or the answers are here in red. How did I do problem 2? I did do factor by grouping. So I looked at the first two terms and saw this common x squared, and I was left with x plus 2. And then I got the last two terms, and I factored out a common negative 25. And I went for the negative because they both were negative. And that, you could move that either way. But then you can see, you're excited because you've got this common x plus 2. I then would factor that out, right? You get the x plus 2 factored out. You're left with x squared minus 25. And again, hopefully you're looking at x squared minus 25 and saying, oh my gosh, I got another step. I have to factor that into the difference of squares. This guy here looks like it factors, in a x squared minus 9 and an x squared minus 5. Right? So you turn this into a quadratic. You really said this was like a squared minus 14a plus 45. And then just factored it, in a quadratic form. This will practice as well more of. And notice here, by the way, the x squared minus 9, you were not completely factored. You need to break that into x plus 3, x minus 3 for the difference of squares. Okay, we've done a lot of work, but this is example 4 is really where we're headed. We want to be able to solve polynomial equations. So here's an equation, right? We've introduced the equal sign. We want to find the solutions. So one way to solve is to try to factor. So to do that, we first set equal to 0. Again, hopefully you recognize, this looks kind of like a quadratic, but it's with x to the 4th, x squared, no x. If I can use my quadratic techniques, I'm going to factor it. Again, please, I really would push you hard to after you factor, to multiply back and make sure you did factor correctly. And here we did. And then you can see that this goes into the difference of squares, right? X minus 9 and x squared minus 1 both factor in difference of squares. And then I set each factor equal to 0 and solve. And finally, the solutions are, and there are 4, right? Negative 3, positive 3, negative 1, positive 1. And, that's for you, Jack. And you should start back here and look and say, look, x to the power 4 gave me 4 answers. And that's pretty interesting, right? A quadratic x to the power 2 gives me 2 answers. We'll talk about that more in further sections. Hey, one more check-in. Can you try to solve this? This looks like x to the power 5. I'm hoping you're finding 5 answers for this one. Here comes the answer. Go ahead and hit pause and hit play when you're ready. And here we go. So first thing I did was set it equal to 0. I then looked at each term and said, hey, I'm factoring out a 2x. I then have this fourth order polynomial that looks awfully quadratic, so I did factor into a quadratic. And then finally, I set each of these factors equal to 0, including the 2x, right? So 2x is equal to 0, which gives me the 0 answer. Then I set this equal to 0, and this is x squared is equal to 3. So x is equal to plus minus. Make sure you catch that plus minus square root of 3. And then finally this one, you could either factor it again or just do the square root of both sides. Hey, wonderful. See you tomorrow in class.